So my talk is a little bit different with the other in the workshop. So hopefully I can kind of like give you something about the new method we try to do with natural language processing, and we propose a method to deal with long sequence. So this is joint work with my colleague and also my collaborator Sterck and our co-supervisor student Yanming Kang from Waterloo. So as you know that nowadays transformer and the other one is diffusion model are the two most popular deep learning architecture. Especially transformer is like one of the up-to-date one, state-of-the-art in natural language processing, in computer vision, speech recognition. And then from the original transformer paper was designed for machine translation task. And then OpenAI start to build the GPT series, and the most recent one is, I believe, GPT-4, which is original of the ChatGPT. So the idea behind the literature about the original transformer, it is an alternative to recurrent neural network to deal with language model. So for the talk, I will focus more in terms of like we can have derive the new way to approximate the attention matrix, and we test our result on natural language processing task. So it's a good idea for me to kind of example some of the LMP tasks that people study in literature. For example, we can filter an email whether it's spam or not. We want to do a grammar check, which is very useful nowadays. Or we can do like a text generalization, which is we want to guess the next word based on the current words, or fill a blank in a sentence, or extracting an answer from a question answering test. So in terms of writing term interpolate mathematical formulation, so when dealing with word, it's only letters there. And the first step we want to do is we want to represent, for this, the input here is a sentence, and a sentence here is represented as a sequence of word vectors. So for example, if I have a sentence that have n words, then each word here is embedded as a row vector with the dimension D model. When we think about the D model here is actually the size of the dictionary. And a simple way to kind of encode a word in the dictionary is using, for example, one hot vector, where you put 0 everywhere except number 1 at the position of that word in the dictionary. Of course, there's some other method to do the input embedding to input a word that contains all the letters into a numeric number vector. And the goal here is we want to learn some embedding Y of the sequence. And what is Y? It depends on the LMP task that we are talking about. So in terms of how to learn that representation from the basically given an input of which is a sentence, and we want to find out some information from that sentence. So before the transformer, then the most popular one, it is a recurrent neural network, where we kind of like based on the information from the previous output of the recurrent neural network, and then wait for the coming words are coming in, and from there we want to predict the next embedding Y. The problem with the recurrent neural network, which is kind of well known now, it cannot be parallelized. Which means that it needs to beyond the word recurrent. You already can feel about that. So in that case, then we couldn't do the parallel, and then because of that short memory, then sometimes if you have a very long sentence, then at the end and at a certain stage, then you may forget what is really happening at the beginning of the sentence. Another approach to want to scale the problem is using the convolutional neural network layer, which is inspired by working with image processing. So the idea of convolutional neural network, for example, if we want to do the convolution layer of size 3, the idea here is we want to find the kind of group all the close word together, and from there we want to kind of find out some information from the whole sentence, where we have a sliding window throughout the whole sentence. And that we know that the benefit here is CNN can be parallelized, but on the other hand, it don't really tell us about, because when we have a sentence, every word in the sentence depends on each other in one way or the other. So using a convolution of a fixed code filter might not be ideal to capture the whole content of very long sequence. And our target here is to work with long sequence. And an attention layer in that context, basically it is xt here is a given word in the sentence, and then k and v are two other sequence. And I will give you some example what does it mean by k, v when we only have an input, which is a sentence. And then we want to find out the relation of that word with those two other sentence to find out what is outcome y. And the benefit of the attention lay here because basically it think about it as like searching for the whole sentence to find the relation. Therefore, it can handle long range dependency very well. So I want to kind of write down the function representation of the vanilla transformer model from the input to output in terms of like. And as you can see, that is a bunch of matrix multiplication with a linear and quadratic term and also nonlinear. So the original transformer is like from the paper attention is own unit, and then it contains comparing with like the previous architecture in neural network. Then it also shares the like the structure of encoder, which is a part on the left, and the decoder, which is a part on the right. For me, I just think about it is like different way of writing the function with certain modification. The number n here is for the way we think about it is like we repeat each of those blocks 6 times in the original transformer paper. And then the add part here, which is popular nowadays, which is the skip connection. Basically, we the outcome of the previous the outcome of that step we add with the original from the input or the weighted projection of the input, so that we can which is like from ResNet. And the idea is to like mitigate the vanishing gradient and have some connection with numerical differential equation. Okay, so and then the norm here, which is a layer norm. So layer norm here is similar to batch normalization, where we want to make sure that for every word in the sentence, which is a row in the matrix, then we want to normalize so that it have a zero mean and unit variance. Of course, I own the empirical value over here. So those are the kind of thing that is similar in terms of comparison with the other like feed-forward neural networks that you can see over there, including the feed-forward, the adding the skip connection, and the normalization. But as you can see from the original architecture, that there's two parts that is make like the transformer is different with the other two, which I think is two key features of the transformer. It is, first of all, it is a positional encoding. Because we are dealing with sequential data, so the order matter. So if we say that a like cat with dog or like that dog chase cat is totally different topic. And then we want to have some way to capture the order of a sentence in the sequence, and it also can see it in the diffusion model. And the second one that it is make the transformer different with the other one, which is the multi-head attention or the mask multi-head attention. So first of all, let's see what the formula it look like. Okay, so for the attention mechanism, that is like it's based on a very kind of the formula here that's saying that given three matrices Q, K, and V, and the relation between those two here is basically when we say n query, which means that like each query here is one row vector, and then Q and K here have the same number of column, which is the feature vector, and K and V, you can think about it coming from the same database, so that's why they have same number of rows. Now, the attention between Q, K, and V is defined to be first, you want to compare the similarity between any row of Q with any row of K. And from that, we do the submax to kind of like think about it as a probability vector, so that's the summation of those coefficients equal 1. So in terms of the, like in the vectorized form, then if you think about it is you have a given a query, which is a vector, then the outcome we want to get is the attention QTKV. As you can see on the right-hand side, with this formula, it's very simple to understand. It just means the linear combination of all the value in that is given, where those coefficient here is decided by the similarity of the given Q with every keys in the given case. And the Z here, that's like the constant to normalize, so that when you add it up on those coefficients, then you have 1. Okay, so, but like, sorry, it's a long introduction about what's going on, but I just want to make sure everyone is the same place. So, but when we talk with language, then the input is a sentence. So what is QKV in that context? So I want to clarify the example. What does it mean by QKV in the input when you have a sentence and then what is the output? So the QKV is like from the database perspective. So think about it as Q here is basically a product that you just like very creatively create and you want to sell that product on Amazon or Marketplace. And then from that product, you want to say that what a price I should assign to that product so that I can sell the product fast or something. So in that context, then the key here you can think about it is like potential category that the product will belong to. And then for each of those like category, then there's a corresponding value associated with that key. Then based on similarity between the given query with all the like category that you have, we can find some kind of like probability weight that assigning how likely does the query belong to that category and etc. From there, that they're doing a simple linear combination of those weights, we can assign the value of the product. So in terms of like really dealing with the LMP task, like language processing. So of course, I talk about it as a simplified version because technically it had to pass through a bunch of like linear, non-linear term. But in simplified version, we can think about it here. Q here is the current word in the sentence. And K and V here are like both the collection of all the current words. And then for the task of you want to predict the next word from all the given word in the sentence, then you can think about the attention in the simplified one. Basically, it is you want to compare the similarity of the current word with all the previous words in the sentence to decide what the next word should be, to make it like the sentence like make sense and like as a normal sentence. So that is some modified example. So in the actual coding, when we talk about the transformer on the transformer model, the Q, K, and V depend on the text. For example, if we do about cell attention, which is the text generalization, then Q and K and V are we think about it as the linear modify or linear transformation of the input X, where X here we can think about it as the encoded vector of the sentence. The reason we want to do that linear transformation, there's a couple of folds. But first of all, it is the idea behind the attention is you want to pay attention to any word with the other word in the sentence. If we just do QK transpose when Q and K are both the X matrix, then likely you only put number 1 on the diagonal, which is that word, pay attention to that word, which is like not ideally for certain application. So that's why I want to say that like when we modify, which is mean that we want to see the linear combination of those rows together. And the other side it is when you look about X, which is the input data in the sentence, which is a sentence, then the D model, which is a side dictionary. And the dictionary, for example, English dictionary is huge. So the size of D model would be very large. Then by multiplying with the matrix, then we can reduce the dimension by like doing the dimension reduction on W. And those W will be learned. Yes.
What is W exactly?
The W?
Yeah.
Oh, those kind of like the matrix that we need to learn, which is a parameter of the attention that we will train through the optimization method that we want to choose. But X here is the input that is given to you.
So you want to find W to replace Q with?
Yeah, so for the attention layer part, then like the input is X, and then they want to learn all those kind of like linear combination of those words to find out what is the next one is. But it's not really linear because it's also processed through softmax and etc. And as you can see from there, one notice is if you think about Q here X and K here X, then when you take the inner product between Q and K, we are going into a quadratic form of the input data, which is make it different with the fit for quadratic network when the input is like the linear in terms of the input data. Yeah. Okay. So now let's put everything together. Then let's write down the equation. So basically, the input here basically is a matrix where n here is number of word in the sentence, and D model is a dictionary side. And then, as you said, because we know that from the attention, it doesn't capture the position, so we add with the positional encoding. So the positional encoding, should be the same size as the input vector over there. And then, if we don't want to learn the positional encoding, then we can use a fixed one. And so in this fixed one, then I here representing like to encode like the row I, which is like what is the positional of the word I in the sentence. And then it's encoded by the sine cosine function. And the J here just capture all the different wavelengths so that you can recover. Or the other one is you can learn the positional encoding, which is basically another W that you have to learn. So adding those two together, then we have the first like input, which is X0, which is the addition of the input embedding with the positional encoding. Now, so when we have X0, then as you can see that you have three vector over there. So basically what it means is we just apply the attention to the matrix. Here is like a scale of X with 3 different matrices. So a scale of X at 3 different matrices where all those W here are changeable parameter. So the multi-head is means that like if you have one attention, then the outcome will get another attention. You have a multiple head, then you can have a bunch of matrices and you just concatenate together because the number of rows are the same. So just concatenated like column by column. And then the WO here is just a way to represent just the role of WO, which is also a parametric matrix that you want to learn, is to show that when you add with the skip connection here, then the dimension match. And after the adding the skip connection, then we do the normalization. Okay, so that is the outcome before we go into the feed-forward neural network. So that is the input to put into the first feed-forward neural network. And then I just want to write down the formulation. So basically that is input to put into the feed-forward. And then after that, you just apply a normal formulation of the feed-forward neural network. And in the vanilla transformer model, they just use a 2-layer neural network. Basically, it's like linear, nonlinear, linear, and another nonlinear. And then you add a skip connection and then normalization. That could be the outcome of the case encoder. And if you do it, like for example, in the vanilla, what you do 6 times, then the outcome of that you can put into the decoder part. So the decoder product is kind of the same as the encoder. And then as you can see, if I just compare the part on the top here, is everything is the same. Like have some input coming from the encoder part, and then you pass through the multi-head attention and then do the normalization. The only difference in the decoder part, it is the mask multi-head attention. We don't need to have it all the time. It's just more or less like depend on different tasks. So for example, if we want to predict a word, the next word in the sentence, then we don't want to pay attention to all the future words. So in that case, that's why we want to assign the value on that. So what is this matrix here? It's just matrix like QK transpose. And then we don't want to pay attention to the future word based on the value. So that's why we add by the minus infinity. When you take the exponential, it becomes 0. Okay. Yes. So that's why the mathematical formulation of the whole like transformers. And then the complexity we care about, we want to the bottleneck of the transformer. The nice thing is because the idea of every Q is measure the similarity with every K, so we can handle long-range dependency. But the trade-off is when you multiply all those Q, K, which basically all row of Q and K together, then the cost here is of order n squared d, which is very costly when n here is the sequence length of the sentence, which is could go to like 1,000 with the current ChatGPT. And then our goal here is actually we want to reduce those time and memory. Time is okay, but memory is really a big thing because a GPU only can, with the current technology, I feel that memory couldn't handle too large, and especially for the university research, why we only can use maximum 4 GPU at a time. So we really want to save the memory. Yeah, so that to put in the context then, and that is the perspective of computationally, but in terms of like naturally, when you deal with a long sequence, long sentence, then I mean when you generate when you want to do the translation on long sentence, then the idea behind what we want to work with long sentence is just because which a lot of people are working on too, is basically if we improve the lexical cohesion or anaphora of the whole text. So that's why there's a need to develop model to handle long sequence. But however, for the one that's before the the ChatGPT, which we don't know the open source, I think, yet. So for the original GPT, the sequence length is only 512. For BERT from Google, it's 1024. For GPT 3 is going to keep increasing, 2048. And then according to the doc from OpenAI, I think, then the GPT-4 here is 8,000, 8K. And then, but like the modified, the turbo version is come to like 100,000 word in the sentence. Okay, so the goal of this work is like we want to kind of like see whether there is a way to attempt to reduce the complexity of like from ON square to ON log n or ON, which is there's already a bunch of work in literature that work on efficient, what they call is efficient transformer, and they divide into different kind of group where they can talk about like they want to, so the idea behind here is like we have to decide which queue is like we pay attention for which key, and there's a bunch of ways to doing that. And the best way to kind of like have an understand what's going on is looking at the matrix QK transpose. So think about it, that is the matrix, that is QK transpose. And the way I think about it is the index on one side is the index of Q, and the index on the other side is index of K. So whenever you see like a blue or white color, it means that that Q is pay attention to only that key from the previous. So the task here, it is for the autoregressive task, which means that you don't pay attention to the future word. So that's why we only see one part of the matrix here. So the first part, that is the original transformer, which basically is saying that every word pay attention to every other word in the sentence. For the sparse transformer, one of the first attempts try to do the efficient transformer. Then the way they do is you want to say that one word will pay attention to the closer word nearby, and then maybe some word a little bit far away. So that's why you see that like every word here pay attention to the close by from the previous, and then to capture the long like dependency, then at a certain jump, like after n word, then you can pay attention to that word with that key. So basically that's why you see those try happening over there, which is happened for the sparse transformer. So the benefit it is like of course, the complexity of sparse transformer is only of order n square root of n. But on the other hand, we can see that some, if there's some case that one word here is like have a dependent on the word that is not in the pattern that you are captured, then likely you don't really capture that important information. Okay. So there's also some other like group of efficient transformer when they should do some kind of like downsampling by the convolution. So downsampling here is like I highlight the big word because they kind of like one of the successful one is like pay attention to the nearby convolution. So in this context, you see both the value, both the at the lower part and the upper part, because we want to give an example in like bidirectional language model where we want to, for example, fill a word in the whole sentence. So we want to pay attention to all the word in the left and on the right of that word. So in that context, then the matrix QK transpose is defined by saying that decide how the Q is attend to the key. Basically, we pay attention the Q pay attention to the key of every in the neighborhood, and also some random happening over here. Basically, to avoid like what happened if we don't capture some information, then we can say that I want to pay attention to the randomly choose some location that key may pay attention to that key, and then also along the range of those two and combine together. That's why we have big bird. There's some other methods that I want to mention. Besides, another idea here is trying to say how we can reduce the order of QK transpose, and also there's some method using the random feature method. Okay, so that's enough. So I talk about what does our method look like. So the motivation of our method is we want to, the same thing with the other efficient transformer, is want to derive the like efficient computational technique to make the memory and the computational cost of the large context size manageable. So we want to achieve the same kind of complexity in time memory from to ON or ON not N. And we couldn't go beyond ON because we have a and word in the sentence. So at least we have to go through all those words. So ON is the first one. And then the intuition behind to design our model, it is basically we inspired by when we read a long book. Like when we read a book, then we may remember the content in that chapter or in the first few pages that we are reading. But for the previous chapter, we may see here, remember something, but not all of them. So that's the idea that we want to say, that we want to pay attention to all the things from the past, but maybe somehow we kind of average information from the previous chapter. Like kind of we could think about it as like some learned kind of like combination of the content in the previous chapter. So that is considered to be a hierarchical context summarization, where we pay attention to, for example, when we are at a certain query, then we want to say that we pay attention with all the key, like close by in the neighborhood. For the one far away, so depend on how far it is from that current word, then we can see how much I want to kind of place downsampling the information. So for the, which we call this, so in the level 0, which is a find out level, then the query I is pay attention for all the key nearby. In the level 1, which is the next length of 1, which is a tree structure happening over there, which is a little bit far away, then we just, instead of paying attention for every word in the previous, we just take an average. And it's not like the average when we decide it is a fixed average, we use a learned average, which is easily to do by a convolution one day with a try, where the word is learned. And then for the information a little bit further than that, then we just use a bigger group to do the sampling. But based on the idea that the far away content, then this is less important to that current word than the other. So I want to highlight that in the way of finding those words, then we use the learned downsampling word by taking the convolution of the key with the content. Okay, so in terms of structure, then how we do the computational part. So we build the structure. So basically, we want to build the QK transpose. So for the QK transpose, so to like really writing down the equation. So for the file level 1, which is for, and then the next one, the way we do it is inspired by, I'm going to talk about it later, which is the Fast Multipole Method, which proposed by Greengard. So basically, we divide the group size, which is M. So the group size M here will decide how much I want to pay on full attention for the first one. And then for the next level, which is doing the level 1 first averaging, then we just group all those keywords in those one together in the first M words, and then do the averaging and represent those one by either one number, or if you want to have a low rank approximation, then you represent that whole M words by like P are the word vector, where P is much smaller than M. In our current context, then we kind of do the fixed one. Like basically, we don't do the adaptively. We just divide from the first word in the first word and the sentence to the last is like divide M, and then for the second level, then this like increasing every time next time by double. And then we just building that like hierarchy structure. Then we can identify on the key by multiplying Q with the averaging of K at different level. And then if we want to really chase down on those, what Q, what J, then we can easily find the formulation easily. Okay, so basically our modification approximation of the QK transpose, it is given at every kind of like entry of QI, and then KJ is defined by how close you are with the current one. Okay, so in terms of maybe visualize that, then you can see that for the file level 1, then we just compile Q and K, and then with like at most 3M words around that one. For the first downsampling one, then what we do over there, it is we represent each group of those downsampling by one number, and then we just multiply Q with that K. So that's why you see those one over there. That is the approximation of QK transpose. And then after that, we apply submark, and then we multiply with the corresponding downsampling of V using the same index, and then that's added up together. We can have an approximation of the attention matrix. So because of that tree hierarchy, where we can keep increasing the level by the order of 2, that the number of level you have maximum could be like log 2 of N over M. So for the simplicity, we assume that the sentence length is N, and then the group here, which is M, is divisible of M. and it's of order 2. So combined together, that is our structure of the matrix QK transpose. So as you can see over here, where there's no dot, it means that pay full attention. Like that Q compete exactly with that K. But far away, then you just represent that, for example, those two words for the group of 2, then just represent one number for those 2. And of course, you can increase M, larger is better. So we can see that somehow has some kind of sparse structure happening over there in certain contexts. And then for our kind of like FMA, it's easy to switch between like unidirection or bidirection, which is because all we have to do is we just forget all the information on top. So that's also the reason why we already do the full adaptive of the location yet. Okay, so some other related work that we can see that we exciting about is actually it also has the inspiration from the Fast Multipole Method and fast summation from the n-body physics that is proposed by Greengard and Rocklin from 87, and then that is used to work a lot in solving partial differential equation, and also what I can say is like the idea of fast multiple method is you can achieve the error as small as you want. So there's some other kind like also modify it depend on different viewpoint of hierarchical attention mechanism that I will not talk too much about here, but which is one is similar, almost similar to us. They're called hierarchical matrix transformer. So the idea is also they go based on the distance from far and away, and the way they interpret is they use a fixed averaging, and they don't do the adaptive one. For the multi-range solution is based on the adaptive wavelet. So the multi-relation one basically says that for the matrix attention matrix, you can represent as a linear combination of like wavelet function, and then it will choose which coefficient to be appear. But both of those two, they only use the fixed weight, and in our case, we learn those weights, so we have some gain, which we can show in numerical results. So we have both some kind of like simple analysis of the error approximation. It is saying that what is the approximation if we want to approximate the full QK transpose with our FNA, what the error look like. So it is based on very simple calculation, also inspired by from the previous work. Then we can say that if C here is a full attention matrix and C tilde here is our approximation QK transpose, then we can bound the Fourier norm of the difference by M, which is what is M in this context? Which is the number of levels that we have in the context, and then the alpha here that think about it what is and then the kernel weights here are normalized with the sense that the summation alpha j here equal 1. Then we can say that the norm here is basically the term that we can control based on the data. It is the M and beta 1 and beta 2, where beta 1 here is upper bound on the norm of the query, and the beta here, which is easy to control, it is the difference of the K. So you can think that if beta 2 here is going to 0, in other words, it's saying that like if we don't require all the K to be the same, we just require that all the K belong to the same like group sample that we are doing. They are close to each other, which is like basically if we have a key that a lot of keys are similar, belong to the same group, that is small to, and that's close to 0, then we can say that the approximation here is going to 0. Yes?
So beta 1, beta 2 tells you how to group them?
Sorry?
Beta 1, beta 2 tells you how to group the levels?
Yeah, like it is a fixed scheme. So basically, it depends on like for each query, you will decide which, you can have a fixed scheme of how you group the term together, which is given by this formula. So for example, at the row I of the Q query I, and then I can decide like which term that I should group together belong to different level.
You want to group them so that beta 1 is small, right?
Yeah, exactly. Like you do the down sampling, like take an average. Yeah. Yes. And then, but the final attention matrix is exponential, right? Because that's softmax term. So we also have an estimation of the exponential of that attention matrix before, like which is the part before multiplying with the value, and it's also can be derived based on some information about the norm of Q and the difference in K. And in this context, we can extend the result to like the full level, like n plus 1 level of the FMA. And then with delta K here, you can think about it as some characteristic belong to the to that level. And then we can see from there it is the delta K, if delta K here is decaying, which is the scenario that we see a lot in fast multiple method, then the error in terms exponential here also becomes small. So that is the takeaway from our analysis. In terms of numerical experiment, I think I will go with that quickly. Basically, it is we're going to focus on two types of language model, which is a pre-trained language model, which means that we deal with unlabeled data. And the data we are working on is the Wikitext 103 and the on Wiki 8. And then the two types of language model we are talking about here, first one is like the autoregressive, which is unidirectional language model, such as the GPT-N series is actually autoregressive. And the model is based on like formulating the probability distribution of the word xi given on the previous word. And we will parameterize that probability as the transformer model. For the bidirectional language model, such as BERT, then we just want to compare the likelihood of that word compared to the other word in the sentence. So that is the difference between uni and the bidirectional one. And to compare the loss function, then we just do the cross entropy loss, where we want to compare. So for example, in the sentence, it is nice to meet you. Then basically what we want to do here for the first sentence, we want to predict what is the next word after it. And then so the target should be is, but like the output from the node what you have is y2. So you want to compare how likely that y2 is close to the word that is given there. So the outcome is comparing the y on the y here with the next word after the input over there. But of course, it's too good to be true that in most of the time, we don't compare exactly that. We compare based on the average slide, which is called the perplexity. So in terms of that context, then we can compare the accuracy based on like, given those the slide, how we can compare the next one, which is based on the averaging of the last S token. So basically, we want to compare the accuracy of the current word with the average of the S word before that. Okay. Maybe I can talk about the numerical experiment now to show. So there's a lot of efficient transformer, as you see in the previous diagram. And the reason why we pick those models is because those models really try to deal with long sequence. So we start with numerical experiment with as two type tasks that we are talking about, which one is the unidirectional, which is autoregressive, and the other one it is a bidirectional one. So and then as a standard, we always compare with full, because full will give you the most accuracy one, but also painful in terms of like the time and complexity in terms of memory. So when we compare, which is our result is the one stand for FMA, then the FMA here, so either if you want to, like in the same context length, like ranging from 500 to 1000, and the next slide we also have it for, they go into 2048 or even 4096. We couldn't go further based on the memory that we have. Okay, so what we see over there when we compare with the other method, then we are second on the as the best. Basically, the right after the full attention in terms of the accuracy. So BBC here, you can think about it as like a measurement to compare the accuracy of the model. And in terms of memory footprint, then we are always one of the lowest one compared. So basically, we have like comparable accuracy compared with the full, and somehow most of the time better than the other efficient transformer, and one also will have the smallest memory footprint. If we run it for both until the 4001, 4K, and then 4K and for the other one, it couldn't run because of the time waiting so long for one experiment to done. For the full one, even 4000 with our capacity of 4 GPU, we couldn't do it with the same batch size. So we have to reduce the batch size by half so that we can run the experiments at the full of memory. So that's why you see the number over there. But it doesn't mean that, as you can see from there, then as we increase the context size, then the memory footprint is increasing, like compared with the full attention. And then we have a very good accuracy. For the other kind of experiment, which is we test in quickie text, and they probably use the perplexity, and then we see the same behavior that we have the like second to the best perplexity compared because full is the best in terms of but in the term of the memory footprint, then we have at least like 3 times lesser than the full attention. Okay, so when we also compare with training with the different sequence lengths and compare with the other model when we don't graph. So as you can see here, the attention wouldn't go much after certain sequence lengths. So that's why we have no more after. Our method is, sorry for the colors, almost the same, but basically FMA here is the purple one, my favorite color. Where that, the pink one over here. Then it's like comparable because like sometimes we don't have enough time to run an experiment like 100 times to really test. So the what we can say over there, it is the memory cost of FMA is like reasonable and scale much better than the full attention. And then as you see from the accuracy is much better than full attention. And then in terms of comparing with other efficient transformer, then in terms of memory footprint, we also the comparable. So to wrap up, maybe I just want to say that there are a couple of things that we want to say here is we derive an official variant of dot product attention with the complexity of ON or ON log N. And the key advantage of FMA is that we compare with other related one is like we learn the weight of the downsampling, which we can show from numerical result that is provide a better accuracy. And then because of the flexible of the FMA, then we can have the potential to empower the large language model with the longer sequence length. It just depends. Right now we are trying to optimize our code. Currently, we already work on, my student work on TVM to implement CUDA kernel from, but maybe still have some way to speed up by borrowing the technique that Fast Multipole Method have been working on PDE to the FMA. And then we can easily, hopefully, can extend to multiple dimensions so that we can work with imaging and video. Okay, so that's it, and thank you.